8.1 is entitled Describing Rotational Motion. Now, rotational motion is very similar to linear motion. Linear motion as opposed to rotational. I put this picture of this girl on a merry-go-round because many of us have been on merry-go-rounds, and merry-go-rounds, you can describe how they're going around easy, like how many times does it turn around? How fast is it spinning? Is it getting faster or is it getting slower? So we have all these relationships like linear-wise, like there's linear acceleration. Actually, maybe I want to do that one last. Linear displacement. And there's also linear velocity. So we've got all these things here: displacement, velocity, and acceleration. And we've talked about them linearly. Like linearly, displacement we measured in meters. Velocity we measure in meters per second. And acceleration we measure in meters per second. Meters per second squared. Now, rotationally, we're going to talk about how far does something rotate. Like if you've got your merry-go-round over here, if it rotated from here to here, we have displacement. Normally, if you were talking about degrees, you would say this rotates 180 degrees. But unfortunately, in physics, we don't use degrees. We're going to end up using radians. So we may need a refresher on exactly what radians are. It's a measure of angular displacement. Velocity, it's going to be radians per second. And acceleration, you may have guessed, is going to be radians per second squared. Now, there's some equations that relate linear to rotation. So you can take something that's linear and you can relate it directly to rotational. There's three equations. You can use linear displacement equals the radius times angular displacement. This is the Greek letter theta. It represents angular displacement. There's another one for velocity. Linear velocity equals r times angular velocity. This is a Greek letter, omega. It's like a W with a loop in the center. It means angular velocity. It's in radians per second. And then acceleration, A equals r times alpha, which stands for angular acceleration in radians per second squared. So let me give you a quick, how do we convert between degrees and radians, because you're probably more familiar with degrees. And then maybe how do I apply each of these three equations right here. So the first thing you need to know, there are 360 degrees in 2 pi radians. So one rotation. And for people who are wondering, there's another, it's called gradients. There's 400 gradients in one rotation too. That's just kind of off to the side. We won't really end up using this, but in case you ever wanted to know or came across it, 90 degrees equals 100 gradients, so it's kind of actually an easier way to do angles. But another useful thing, 180 degrees equals pi radians. So a lot of times, if you've got, let's say, like 97 degrees, and you want to turn that into radians, what I would end up doing is dimensional analysis. I'll put degrees on the bottom and I'll put radians on top. And I'll say that in 180 degrees, there's pi radians. So you just take out your calculator and you take 97 times pi, so 97 pi divided by 180 will give you 1.69 or 1.7 radians. And if I had something like radians, if I had like 52 radians, change that into degrees. So I would start with 52 radians. I'll put radians on the bottom and I'll put degrees on the top. And I could say in 360 degrees there are 2 pi radians. So this is another way to use that dimensional analysis. So I take 52 times 360 divided by parentheses 2 pi. And you get 3,000 radians. Oh, I'm sorry, degrees. It's quite a few rotations. 3,000 degrees. Just to give you an example of how I would use these equations, your book has a couple of example problems. So maybe I'll just do, let's see here. Maybe I'll do number 9, for example. It deals with angular acceleration. Number 9 says, in the spin cycle of a clothes washer, the drum turns at 635 revolutions per minute. If the lid of the washer is opened, the motor is turned off, and it takes 8 seconds to slow to a stop. That looks like a time. Believe it or not, what this is a velocity, angular velocity. Because even though it doesn't say radians per second, I can easily change it into 8 radians per second. So I can take 1 revolution is equal to 2 pi radians. So that way the revolutions are gone. And I can take 1 minute and change that into 60 seconds. So I can end up getting this in radians per second. So then minutes cancels off. So I take, let's see, I can't see it. 635 times 2 pi divided by 60. And I get 60.5. 66.5. Radians per second. So just like, I think I could maybe use my this equation right. No, not really. I was thinking I might be able to use this equation right here because I'm looking for the angular acceleration. I don't know the radius, but here's another fun equation that we can use. Just like we have velocity equals distance over time, we can use angular velocity equals angular distance over time. And just like we use acceleration, I mean your change in displacement over your change in time equals your change in change. So acceleration equals your change in velocity over your change in time. So too does angular acceleration equals your change in angular velocity over time. So this is actually the horse I'm going to use here. A couple more equations, but it's very similar to the linear side. So my angular acceleration is equal to my change in angular speed over time. And since it takes 8 seconds to change 66.5 radians per second, So I take 66.5 divided by 8, and I get 8.3 radians per second squared. Maybe I'll do one more example for you before we go. Going back here, how would I maybe relate look at number 2 here. Number 2 says a truck has a linear acceleration of this, and the wheels have an angular acceleration of that. How big are the truck's wheels? Here's one where I'm trying to relate angular to linear. And so that's that third equation. Linear acceleration is equal to the radius times angular acceleration. And it's pretty simple. This goes here, 1.85. The radius, angular acceleration goes there, 5.23. And it's got to be in radians per second squared. So I take 1.85 divided by 5.23, and I've got 0.354. So the radius is equal to 0.354 meters. But the thing says what's the diameter, so you got to double that, and you get 0.707. So the diameter, 0.707 meters, or 70.7 centimeters. So in summary, describing rotational motion is really, really similar to describing linear motion. We've got linear displacement, and we've got rotational displacement. Linear velocity in meters per second, angular velocity in radians per second. Linear acceleration in meters per second squared, rotational acceleration in radians per second squared. So if you spin something and it's getting faster or slower, it has angular acceleration. If you spin something at a certain speed, it's got linear velocity. And how many times it rotates? Linear displacement.